In this video, we'll continue our discussion of section 7.2. What we're going to do in this video is that we are going to find the Laplace transform of a first derivative, a second derivative, and then use that to make a rule. All right. One thing I do want to remind you of is that the Laplace transform of f of t, we note that capital F, and then remember it becomes terms of s. Okay, so we're going to use this notation here in a sec. Okay, so we want to look at what is the Laplace transform of our first derivative. All right, so we're going to use the definition, remember, which was 0 to infinity of e to the negative st times f prime f of t dt. So that's just using the definition and plugging the derivative in. What we're going to do from here, there's really no way to move forward because we have t's in both. We have two functions. So it would make sense for us to go to integration by parts. All right, so we get u, du, dv, and v. Now, if I'm breaking that down, I think it makes the most sense to put an f prime of t here, dt, because taking the integral back, I'm just going to get f of t. That's really nice. So I'm going to do that. So if I do that, then e to the negative st goes here. So it's just a derivative. We have negative s e to the negative st. Remember, it's in terms of t, so that s is a constant. Okay, so now we can go take this and it can become e. So remember, it's uv e to the negative st f of t. And we're going to run this thing. And remember, it is in terms of t. So t equals 0 to infinity. Plus, remember, it's just a limit, but we'll be okay just for this argument. And then it's going to be, so it's u times v times v du. So that's why we have a plus. We pulled that s out because this is for t. So this is going to be s times the integral from 0 to infinity of e to the negative st f of t dt. All right, and that should, this little thing right here should, hopefully you're looking at it and you're like, well, that's just plugging into the definition. So this is just the Laplace transform of f of t. So I'll be able to change that to that. And then the first part, if I plug infinity, remember it's a limit, so we're not really plugging infinity in, right? We're thinking about the limit, but we can save us some time. If we take the limit for t going to infinity and I have that negative power, remember that goes to the bottom, that's going to create a 0. Meaning, the only thing I'm going to get is negative, and then if I plug 0, I'll just do it, negative e to the 0, no negative now, it's just 0, times f of 0. We did a minus out front because it was the lower bound, meaning I had to minus that. All right, and then plus s times L of ft. Remember, that's what was in green here. It's the same thing. Or blue, I guess. Forgive me. Okay, so we have that, which means that we actually have a definition here. E to the 0 is 1. We get negative f of 0, plus s times Laplace times s of Laplace f of t. Okay, so I'm going to write down that definition. The Laplace of f prime is going to be equal to, I'm putting that the positive term up front, f or s, f of s. Remember, that's what we call, we can go ahead actually in our notes, change this to f of s. That's what that is. All right, so there's our definition, and then we minus f of 0, whatever that is. So if you see f of 0 here, that means we're probably going to be using some kind of IVP. And you would be correct. Okay, so there's our first rule. That's first derivative is that. So now we're going to do it for the second derivative and then make a conjecture about the nth derivative. All right, so Laplace of our second derivative. So we're just going to plug that into our definition, 0 to infinity of e to the negative st times f double prime of t dt. Again, it makes sense if I have two functions like this to do integration by parts. So u in this case will follow the same trend that we did last time. I got e to the negative st. So that means dv should be f double prime of t. That also helps us out because that's an easy integral. That would be f prime of t. All right, going back one. And then again, this derivative, same thing. No surprises there. Right, so integration by parts then we'd have e to the negative st f prime of t. That's u times v. And then remember, we got to plug that in from 0 to infinity. Okay, and then we're going to get it's u times v minus v du. So I'm going to have a plus. That s comes out, it's just like last time. And then we're going to have the integral from 0 to infinity of e to the negative st times f prime of t dt. Okay, so this thing here, well, that thing is just the Laplace of the first derivative. So, okay, I'm going to rewrite this. We're going to mess with this a little. Same kind of thing happens here. Infinity, if we took the limit as t goes to infinity, the whole term for this part goes to 0. If I plug in 0, I'm going to get a minus. E to the 0 is 1, so I'm going to get a minus f prime of 0 plus s times the Laplace of f prime of t. And we can use that definition that we just came up with to figure out what our definition for the second derivative will be. We're going to get a minus okay, so minus f prime of 0 plus, and then s times the Laplace is s times f of s minus f of 0. All right, so let's move those things around. This is going to become, okay, do you see I have s times both of those? So I'm going to get s squared times f of s. And then I'm going to get a minus s f of 0. Right? And then we minus our first derivative. So that is our definition for the second derivative. All right, so f double prime of t is going to be equal to s squared times f of s minus s times f of 0 minus f prime of 0. There is a pattern here. I don't know if you see it. Um, let's try to write our third derivative. Laplace of our third derivative. I have some bad notation. That's not supposed to be there. Sorry, I think my brain was just moving forward too fast. Some of you guys were probably yelling at me. So don't do that. Go ahead and fix that. And then the Laplace of our third derivative. We're not going to run through the definition again. We're just going to use some, if this was the top one is our definition for the first Laplace of the first derivative, then the Laplace of the third derivative. All right, that's going to be, notice if the second derivative started at s squared, then this one's probably going to start at s cubed. And then this is going to be times fs. Notice that was the same in both. And then we're going to subtract out until all the s's go away, so s squared. And we work our way up f of zeros of our derivative. So the next I'm going to have s times f prime of 0, and then I'll have one without it. That's just f of 0. We work, or f double prime of 0. So we work our way all the way, the s's go away, and then f of s goes to f of 0, then we go up derivatives until we are settled. So if we had to write this as a formal definition here, let's try it. The Laplace of the nth derivative of t is going to be s to the nth power times f of s. And then we're going to go down minus f in minus 1 times, and then we just start with our function, f of 0. Then we go down again, s of times f prime of 0. And then now we can extend this into as far as we need to. I'm not going to go up, I can't go up to n, right? So I'm just going to write plus dot 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 dot. It goes on, and then it's going to get minused again, and we'll work our way all the way down to f. And notice the derivatives up here. Like on this one was 2 when it was the third derivative. So it's going to be n minus 1 derivative of 0. Okay. And this is, oh, I forgot my power here. That's n minus 2. We would work all the way down until we would get, we have f to the 0 there really at the end, or s to the 0. So it walks down. So there are definitions. We could summarize the 3 that we have. We could do it here. All right. So we will be taking, this allows us now, if we think about this, if I can take the Laplace transform of any order derivative that I have, then if you take a diff EQ, I could take the Laplace transform of both sides. And then that's what we're actually going to do. So in the next couple videos, we'll have 2 examples. Taking a diff EQ, taking the Laplace transform, it will take us to an algebraic equation. We'll solve the algebraic equation, and then we'll take the inverse Laplace to get us back to our answer. So we'll do that in the next 2 videos.